let's just manipulate this integral form term by term. The first term, we know that if I integrate a time derivative, if I have it's multivariate calculus again, if I have a function u being a function of x and t, if I integrate a time derivative over a fixed domain, then I can exchange the time derivative, right, with the spatial integration. It's actually a special case of integration over a and b, integrating over a to b when a and b are functions of time. I mean, you probably studied that in multivariate calculus, but like here, if a and b are not a function of time, this is actually just a d dt of the integral of u over a and b, right? And if a and b are a function of time, there are additional terms that are scaled by dA dt and dB dt. Of course, here a and b are constant, so dA dt is 0, dB dt is 0, so we only have this. Okay, and then the second term, we are integrating now not a time derivative, but a spatial derivative over space itself. We now here invoke the famous, probably the first, one of the first thing you learned about the derivative and the integral, right? They cancel each other. If you integrate a derivative over the same variable you take the derivative to, you get just what? Half of u squared at b minus half of u squared at a, right? Okay. So this equation actually doesn't require u to be differentiable. So because now the spatial derivative is gone, it becomes this, right? This, I mean, there is nothing that requires u to be differentiable. And the time derivative becomes this. Oh, there is still a time derivative. But actually, this is a weaker, the derivative of this, the time derivative of the integral being existent, is a weaker requirement to u itself being differentiable to time. I'll think of just to take as an example of a solution like this. If I have a shockwave that travels, okay, if I have a shockwave that shifts towards the right, then the solution as a bivariate function is actually not differentiable to time when the shockwave sweeps through a particular point. The time derivative is infinity, right? Suddenly it jumps from the above the shockwave, it falls down to the underneath of the shockwave, or it goes the other way. But if you integrate the solution over any non-zero interval, as the shockwave moves through, the integral actually increases slowly, right? It increases in a continuous manner. So this is really a weaker, although we seem to have derived this equation from the differential equation. We have derived the integral form from the differential form. This is a weaker equation. It has weaker requirement on the solution u. Okay, make sense? Any questions in this? Yes?
So this only applies to the Brooker's equation, but I'm guessing we have to like do this process for multiple equations. This problem. So
yes.
How would you do that generally?
How would I do that in general, right? So that's a very good question. And the short answer is I cannot do that in general. Okay, so I cannot do this to any partial differential equation. But I can do this in general as soon as I can write a partial differential equation into the blue form, right? As long as I can write a partial differential equation in the blue form, then I can just integrate it. And specifically, what do I mean? Let's actually let's actually write it down. So the most general form of differential equation where I can do this is a differential equation described in that way. Okay, du dt plus ddx of not u, but a function of u is equal to 0. That's the most general form of equation where I can just integrate it, right? So if I integrate on both sides over dx a to b, that is always gonna give me not partial anymore. I have a d dt of integration of a to b of u dx plus now f of u, not just a u squared over 2 at b minus f of u at a equal to 0. Okay, so let me pause a little bit and answer this question in a slightly different way. So your question is, how can I do this in general for PDEs, right? And the answer is I can't. What I can do this in general is for actually physical phenomenon that describes the conservation of something. Okay, conservation of mass, for example, conservation of momentum, conservation of energy, conservation of chemical species, conservation of anything.